In this video, I'm going to go over an example of how to calculate the displacement in a truss using the virtual work method. And these displacements are going to come from three different sources. The first is going to be from loads on the truss. The second is going to be due to temperature change for select members in the truss. And the last one is going to be due to a fabrication error where one of the members is fabricated too short. So here we have our sample truss with 6 truss members. We have the same AE for all trusses, same area, same Young's modulus. The truss members also all have the same coefficient of thermal expansion, alpha, equal to 12 times 10 to the negative 6 per degree Celsius. Then we're going to find the vertical displacement of this joint, joint A, for these three cases. As I mentioned, the first one is if we have loads on A and B. The second is if members A, B, and B, C experience a temperature increase of 110 degrees Celsius. And the last one is if this member AE was fabricated to be too short, and therefore the members have to be deformed in order to fit that truss member into the truss. So first I'm going to use the slopes in order to calculate my truss forces. So it's nice to know that we have a ratio of sides here, and all of these triangles happen to be the same. So the bottom, if the vertical is 1, then the bottom is 2. So this length is 2 times the height, and then the diagonal would be 2.236. Now I'm not going to go over the truss analyses for all of these trusses, so you might want to check out my other video where I describe the section of joints, which is the way that I solve these trusses. So in this method of virtual work, we have two systems. One is a real system, and in that real system we want to know the real deformation at a point, which is what we're solving for, or it could also be a rotation if we're talking about a beam. And we also need to know the real deformations of each of the members. And these are known because we can calculate them based on the forces in the members, or sometimes those deformations might be caused by temperature or fabrication error. And then parallel to that real system, we have a virtual system, and we select that virtual system conveniently such that we can calculate the unknown external deformation in the real system that we're looking for. So for example, in this case, we always want to find the deformation at A, so we're going to construct a virtual system that has a point load, a unit point load applied at A in the direction of the deformation that we want to find. So in that virtual system, we need to know the external forces that are applied, which we define as being our unit load in the correct location, and we also need to know the virtual internal forces, which we can find based on that external force. So the virtual system is going to be the same for all three cases, because in all of those cases we're finding the same unknown, which is the vertical deflection of joint A. So what we're going to do is add a unit load to A and then find the virtual forces. So here's our system. Looks something like this. And we're going to add a unit load of 1 kilonewton at point A, and then find out what all the forces are in these truss members. So I've gone ahead and done that using the method of joints. I did it right on this diagram. I didn't draw all the joints individually because this is a pretty simple truss. So I've labeled all of the forces on each of the members. Here is member A, B, C, D, E. And I've also labeled whether they're in tension or compression, because that's important for our virtual work. And I've labeled that two ways. One is with these arrows. When they point away from the joints, it's tension, and when they point towards the joints, it's compression. So the convenient way to draw these arrows is to draw them with respect to which way they act on the joint, because then you can do this method of joints without having to draw each joint individually, because we have a little equilibrium set up at each joint, where we have this external load, for example. We have this tension load pulling to the right, and we have this compression load pushing down and to the left. So we have two zero force members here, and these are our reactions. On this side, the reactions are external loads, but since the deformations at that point are 0, because they're pins, then they're not going to contribute any work. So the only virtual external load that contributes work is this unit load that we've added here, that we've defined. So this is the virtual external force. And these guys on each member are the virtual internal forces. And these are all of the things that we need to know from our virtual system. We don't care about any of the deformations from our virtual system. We only care about the deformations of our real system. So if we go ahead and solve the first case, which is our real system with the applied loads. And that system is going to look like this. So again, we have the external loads that we're applying. These are the reactions which are unknown at the moment. And we're trying to find this real external deformation, delta A. So since I know these external loads, and I know the boundary conditions, I can go ahead and solve my truss. And so again, I use the method of joints. I combine that with the external equilibrium at the reactions to find all of the loads in this truss. And so you can work your way through. I'll leave it as an exercise for you to find these loads for yourself. So again, we have the real external deformation for this real system. And these are our real internal forces. So remember, for the real system, what we're primarily interested in are the real internal deformations, not the forces. So for the virtual system, we're always concerned about the forces, and for the real system, we're concerned about the deformations. But that's okay, because we can calculate those real internal deformations based on those real internal forces. And that's simply equal to FL over EA, where these are the real internal forces. Then this is the length, obviously, and this is the Young's modulus and the area, which we've said are constant for all of these. So now for A, we have our virtual system, which is the same for all of our parts, to find the deflection at A. And then we have our real system, where we found the loads in all these truss members, and we're going to use this equation to find the deformations for each of those truss members. So now the easiest way to go about solving these kinds of problems is to come up with a table so that you can keep track. I'm going to list all of the members by name: B, C, B, E, C, E, and D, E. And so I'm going to list each important thing in order. So first is the length, so I'm going to go and find all those lengths, like so, just from the geometry of the system. Then I have my real internal forces. And remember, these are just a step to find the real internal deformations. So these come straight out of this real system diagram, so I'll put those in. Now for these forces, the ones that are in tension I've made positive because they elongate members, and the ones that that are in compression I've made negative because they tend to make the member shorter. So then in parallel with this, we're going to use these to find the deformations, but I'm going to save that step for later to make it easier. And then in parallel with this real system, of course, we have the virtual system, and there's a whole set of virtual forces, and these are going to come from the virtual system diagram that we made here with this unit load. So all of these forces I'm just going to put straight onto this table. And again, tension is positive, compression is negative. You see we have a few zero force members. That's going to actually end up meaning that these members we can totally disregard. So now, in the end, I want to find my virtual internal work. And the virtual internal work is deformation times the virtual internal forces. The real internal deformation times the virtual internal forces. So I'm just going to add these up for now. So this is going to be FV times FL. So this is the virtual internal forces. This is the virtual internal the real internal loads times the length, and later I'm going to divide this whole thing by EA so that this turns into deformations. So what this column really is virtual work interior times EA, because later I'm going to have to divide it by EA to get the deformations. Okay, and this is also in kilonewtons squared times meters is the units. Okay, so I'm just going to do 2.4 times -10 times 2, and we get -48.0. And then we do likewise to figure out all the rest. So you see, any column where we have a 0 in any of these categories, we're going to end up with 0 contribution to the internal virtual work. So really, we don't even have to find the forces in these if we know that ahead of time. So now these are the virtual work contributions times EA for each of the members individually, and we need to find the total virtual internal work. So we're going to do the sum of this, FV times FL, and that is -246.8, and that's kilonewtons squared meters. And so now we're at the point where we can find our deformation, and we're going to do that using our virtual work balance, right? So we know that external virtual work equals internal virtual work, which is the principle of virtual work. Okay, and our external virtual work, we call that WVE, internal WVI, for example. And we know that this is our external virtual load times our internal real deformation. Okay, so our external virtual load is our unit load that we put on, 1.0 kilonewtons. The real external deformation is delta A, and that's our unknown, right? We don't know what that is. That's what we're trying to find. And then our virtual internal work is 1 divided by EA times the sum of FV times FL. Okay, so you'll recall that deformation is FL over EA. So then this whole expression, the virtual internal work, is the sum of the FV times the delta, which is what this represents. And then this EA here is equal to 200,000 MPa times 1200 millimeters squared, which are the Young's modulus and cross-sectional area that we defined at the beginning of the problem. And if we work this out, this is newtons per millimeter squared times millimeters squared, so these two together make newtons. It's convenient for us to put this in terms of kilonewtons, so we'll divide the result by 1,000 to get 240,000 kilonewtons. So then we can rearrange this equation for delta A, and we get -246.8 kilonewtons squared meters, which is our sum here, divided by our EA, which is 240,000 kilonewtons, divided by our external virtual force, which is 1.0 kilonewtons. Now, this of course could be any magnitude that we care to make it on our virtual work diagram, but it's convenient to make it 1, because then when we divide, we're only dividing by 1 here. So then this equals negative 0.001028 meters. Okay, and this negative means that it's opposite, the deflection is opposite of the direction that we drew our unit load on the virtual force diagram. So we drew this as up, so since we got a negative answer, that means that it's going down, so we can say that delta A is equal to 1.03 millimeters downward direction. And that's all there is to it to find the deflection at A due to the loads on the truss. So in the second part, we're asked to do the same kind of problem, except based on temperatures causing the deformations. So in this case, our real system looks like this, where now we don't have any external loads on the system, but we do have temperature changes on A, B, and BC, which is what was defined. of plus, this is delta T of plus 110 degrees Celsius on each of these. So we don't have to do any truss analysis. We already know what the temperature changes are, so we can go straight to our table. AB, AE, okay, BC. Now you can go through and do all of these, but you've got to know that as you start this problem, since we only have temperature changes, all of the deformations, the internal real deformations of each of these other members is going to be 0. So when we do our internal virtual work calculation, we're going to have a 0 in the deformation column, which means that we're not going to get any internal virtual work, so we can pretty much ignore those. We can actually legit ignore them. So I'll put in my lengths, 2.4, 1.2. Okay, so we have a bunch of other members here that we're ignoring, and I've included a few just to show. Okay, so this is our delta T, and this is real. So we have a real deformation caused by this delta T. On AB we have plus 110, AE 0, BC plus 110. So this one we're going to just end up crossing out. Same with BE, same with all of the ones below. And then we still have our virtual system, which is the same as for the last question, because we're still trying to find the vertical deflection of A, so we still have that vertical unit load of 1 kilonewton. So this is virtual. And these I'm just copying over again from the last table, negative 2.236 plus 2.0. You see this one was a 0 force member in the virtual, so it's double crossed out. Alright, and so now since we're doing a temperature calculation, then instead of doing FV times FL, I'm going to do FV times delta TL. And we'll see how that's going to give us a sum that's going to allow us to calculate the total virtual work. And the units for this is going to end up being kilonewton meters per degree Celsius. So we're just going to multiply these numbers together. So 2 times 110 times 2.4, we get 528. This is positive because all these numbers are positive. And plus 528. Now a note on the direction. These delta T's are an increase in temperature, and we're going to consider that positive in our balance because a positive increase in temperature makes the member want to elongate. So that's the same as if it was in tension. The elongation effects are going to be considered positive. So I'm going to take the full sum of these, sum of FV delta TL, and that's just the sum of these two, which is 1056 kilonewton meters per degree Celsius. And then we're going to do the same thing. So this is our internal virtual work, except without the coefficient of thermal expansion, which we still have to add, which is the same for every member. So that's why I didn't put in the table. So then we have WVE is WVI. External virtual work is internal virtual work. External virtual work side is the same because we still have that unit load, and we're still looking for delta A. And the internal virtual work now is alpha, which is the coefficient of thermal expansion, times that sum, FV delta TL. So you'll recall, so here we have delta is equal to alpha delta TL, which is the deformation of a member due to an increase in temperature or decrease in temperature. Alpha is the coefficient of thermal expansion. And then the delta VI, which is our internal virtual work, as you'll recall, is the sum of the real internal deformations times the virtual internal forces. So the virtual internal forces is here. The real internal deformations is alpha delta TL. So this is our internal virtual work. So we can rearrange this for delta A, and we get this is our coefficient of thermal expansion, which was defined at the beginning. Then we have our 1056, which is our internal virtual work. And then divide that by 1.0 kilonewton, which is our unit load, and we get delta A is equal to plus 0.0127 meters, which is in the same direction then as the unit load that we drew. So that's 12.7 millimeters up. So that's how you do it for temperature. Now the last part of the question asks us, what happens if we have a real system and one of the members was fabricated to be too long or too short? Okay, so we have our system that looks like this: A, B, C, D, E. And we're told in the problem that this member, AE, is 12 millimeters too short. So since it's too short, that means it's shorter. It's been as if it has decreased in length, so that would be equivalent to a compression. So we're going to make all of those negative. So too short is negative because it makes the member shorter. So now again, we don't have to do any truss analysis, just like the temperature example. And this actually is our delta, so we actually don't have to do any other calculations either. And since we only have one member that's affected, the rest of these, the delta is going to be equal to 0. So A, B, and all those other members, we don't have to consider them at all because the delta is going to be 0, so therefore our internal virtual work is also going to be 0. So we really only have one member to consider. Our delta, instead of calculating this, it's given as negative 12.0. So that's negative again because it's shorter. Then we have our internal virtual work for that member. Sorry, our internal virtual force, which is negative 2.236, which is just taken straight from our virtual work calculation up here. 2.236 compression, so negative. And then so here we can calculate directly our internal virtual work, WIV, which is delta times the FV. And this is in kilonewton millimeters now. So keep track of the units. So this is in millimeters, this is in kilonewtons. We could change this to meters so that it's consistent with everything else, but we'll see that in this case it really doesn't make sense to do that. So I just do 12 times 2.236. I get positive 26.83. So therefore it's clear that the sum of the same is 26.83. Now we could have multiple members that are too short or too long, in which case we would add extra rows to this table. And then again, external virtual work equals internal virtual work. Left side of the equation is the same because we're still looking for the same deformation, delta A. And then on the right we have the sum. Okay, and this is directly our internal virtual work. We don't need any coefficients on the outside. And so to solve this equation, 26.83. So now we have kilonewton millimeters. On the bottom, we're going to have kilonewtons from this unit load. So then we're going to get directly delta A is 26.8 millimeters. And since it's positive, it's in the same direction as the unit load, which is up. And that's how you calculate deformations of a truss system using virtual work for the case of loads on the truss, for the case of temperature changes in the truss, and last for the case of manufacturing tolerance issue.